So just kind of highlighting a few basic Saturn data points. Orbits about 10 AU from the sun, about nine and a half on average, out to about 10, into about 9. Eccentricity about 0.05, similar to some of the others. Orbits a little bit less than 29 and a half years. Rotation is very much like Jupiter, about 10 hours or so, a little bit longer on the inside poles than at the equator, so differential rotation just like Jupiter. The tilt is about 27 degrees, and the tilt of the orbit with respect to the ecliptic is about 2.5 degrees. So again, this is really nothing's really unusual or outlandish about all that. In size, it is big. It has a diameter about 9.5 Earth diameters. That's actually quite large. Okay, so that means you could fit an awful lot of Earths inside of it, and so you could fit almost 800 or 900 Earths inside of Saturn. So that's real close to Jupiter, which can fit 1,000 Earths inside of Jupiter. But the big difference is the mass is a lot less. So the mass of Saturn here is only about 100 times, 95 times Earth mass. Jupiter, you could fit 1,000 Earths inside of Jupiter, but it has a mass of over 300 Earth masses. So this is much, much lighter, so the density is much less. The density is 687 grams per or 687 kilograms per cubic meter. That means that is 0.687 grams per cubic centimeter. That means it's actually less dense than water. So that's very low density. Now, part of the reason is that it has less mass. Less mass simply means there's less gravity pulling inward, squeezing all that hydrogen and helium. The more mass you have, the more it squeezes, and the smaller it gets compacted. So again, a lot of books give this so-called surface gravity, which I've thought is always kind of a silly thing because there's no real surface to it. But this is the basic parameters right there. Saturn has a magnetic field. It's nowhere near as strong of a magnetic field as Jupiter's magnetic field, but it is a very strong magnetic field compared to Earth. We know it has a magnetic field because of the ring spokes and because of auroral displays. So it does have a magnetic field. Now, Saturn's magnetic field is not quite as strong because it does not have as big of a liquid metallic hydrogen region as Jupiter. Saturn's very warm at the poles. Saturn radiates more energy than it gets from the sun. Now, this is actually a temperature profile from the Cassini spacecraft, and you can actually see that, interestingly enough, Saturn is coolest right near the equator. Well, why is it cool to the equator? Well, because the rings are shadowing the equator some of the time, and so that makes it cooler. The polar regions are hotter. Now, it gives off more energy than it gets from the sun, but that turns out to be a problem. Kelvin-Helmholtz contraction, which may apply, which certainly applies at Jupiter and may apply to a degree at Saturn, is not going to be able to produce nearly as much energy or heat on Saturn as it does on Jupiter because Saturn has much less mass. And so that cannot be the explanation for all this extra heat. Again, interior structure, Jupiter, somewhere between 3, 4, 5% of the Jupiter's mass, about 2.6 per mass generally given is the core. Saturn has a little bit larger core in terms of percentage of the mass of the planet. That's probably going to be almost the same size mass core as Jupiter has. If Saturn and Jupiter both formed from direct accretion out of the propellant, they should be primarily just hydrogen helium. So most of the material in the core probably comes from comets and asteroids and things like that running into it. And so this would suggest they both got similar amounts of stuff running into them. Okay. You have a core that's going to be rocky core in the middle. So we get a rocky core right near the middle here. You've got liquid ices surrounding that. You've got a mantle that's liquid metallic hydrogen. And the outer parts are going to be ordinary hydrogen. Okay. Once again, just like Jupiter, this is going to exceed the critical point of hydrogen. So what's going to happen is it doesn't really have a dividing line between gas and liquid. The upper part is definitely gas. The lower part is definitely liquid. In between, it's kind of like, well, not really clear what it is. Again, this is above the critical point, so exactly the same argument that I gave in the lecture on Jupiter's interior. Both have similar basic compositions. Okay. Saturn has less mass, therefore less gravity. Less gravity means less compressed. Less compressed is why you have that's why it's almost the same size as Jupiter. So it's less dense because it's less squeezed. Okay. So it's going to have less of a liquid metallic hydrogen region because it doesn't have quite the pressure to produce as much as Jupiter does. There are indications Saturn may have more of the what we call liquid ice. Now remember, liquid ice is not just going to be H2O, but it's also liquefied natural gas, liquefied methane, liquefied ammonia, liquefied CO2, pretty much anything that's normally on Earth when it's ultra low temperatures, it's solid, so we call it gas. In the outer solar system, it would be ice. So in the outer solar system, all these things are solid, so we generally think of them as ice. Even the water at this kind of pressure is not going to behave like you think of as water. So that's why we often refer to as liquid ice rather than as water. Saturn, farther from the sun, maybe a few more comets running into it, so a little bit larger liquid ice region. Saturn's magnetic field is only about 5% of Jupiter's magnetic field. That's still pretty intense still compared to a lot of the other planets, but it's not anywhere near as intense as Jupiter's. Now, the odd thing about Saturn's magnetic field, though, is it's lined up almost exactly with the planet's north and south poles. Now, this is a little bit odd because no other planet in the solar system with a magnetic field has a magnetic field that's lined up with the planet's rotational axis. And so it's kind of almost taken for granted that the magnetic field axis is slightly off. That's not the case with Saturn. So again, that makes Saturn somewhat different. Both Saturn and Jupiter have auroral activity because of the magnetic fields. So here's pictures of the aurora that you have on Jupiter and aurora that you have on Saturn. Both of them, same thing. You got charged particles caught in the magnetic field, running into the atmosphere of the planet, knocking electrons off. As the atoms grab electrons back, you get an aurora. Now, one big difference here is that the aurora on Jupiter and Saturn are going to be different colorations, different spectrum than the aurora on Earth. Remember, on Earth, a lot of the pretty auroral displays are due to electrons knocked off of nitrogen or oxygen atoms. Those are not big constituents of the atmosphere of Jupiter or Saturn. Jupiter's and Saturn's atmosphere are primarily hydrogen and helium. Speaking of the atmosphere, Jupiter and Saturn have different compositions. Now, they should have the identical composition, because after all, if they both formed out of direct condensation, they should have the same composition of the Sun. Jupiter is kind of close to the composition of the Sun. Saturn is much more enriched in hydrogen. And so this was a huge mystery as to how it got so much more hydrogen than helium. Now, it has less mass, and so you would think if something was going to leave, it would be the hydrogen that leaves first, because it's lighter. So what could be doing it? Well, they began to realize that in the outer part of Saturn, in this fluid region in there, it's just about the right pressure that helium can actually form little droplets and go sinking into the interior of the planet. So it's like it's raining liquid helium. Well, as all this helium rains towards the interior, it releases gravitational energy. That gravitational energy heats the planet. So that means that even though they may have the same amount of hydrogen and helium in them, because that helium is raining into the interior of the planet, there's less helium in the outer parts of the atmosphere, and therefore the spacecraft that we send by see more hydrogen in the outer parts of the atmosphere. Just like Jupiter, there's clouds that block our view of what's in the interior, so we see clouds there, but the composition of the atmosphere is going to be slightly skewed because the helium rained inside and released heat in the process. So raining liquid helium. So this is like weird stuff with Saturn. The clouds are pretty much the same kind of clouds you get on Jupiter, but unlike on Jupiter, these clouds are much more spread out. So they're much more spread out in elevation than they are in Jupiter. In Jupiter, they're more compacted because Jupiter has more gravity. You're squeezing everything more. Saturn with less gravity just simply means the entire atmosphere puffs out more. And so because these cloud layers are, the darker layers are much, much deeper inside the world, below the outer layer, that makes them much more muted. And so that's why you don't see the stripes on Saturn as prominently as you do the stripes on Jupiter. They are there, but they're very difficult to see. Now, there are other storms on Saturn. Here's a storm here that's like a 5,000-mile wide storm, which is basically like a giant hurricane on Saturn. 350-mile-per-hour wind, so it's like way stronger than any hurricane on Earth. But it has eye wall and cloud patterns, so it's like a hurricane. So just like Jupiter has massive storms, Saturn has massive storms. And on Jupiter, we have this ring of storms around the polar regions. We have sort of a big polar vortex. You've heard about the polar vortex on Earth. Well, Jupiter has a polar vortex too, and the polar vortex swirls up, and it makes all these storms that are swirling around, going around the pole.